So we're doing exponential models. When I taught this last year in secondary 3, I got a little bit different. And then I taught it in secondary 2, learned a shortcut, and now it's a lot easier. So here we go. So exponential functions, the parent graph or the general shape looks like this. So you're going to use an exponential function when you're talking about growth or decay. So there's a lot of real life examples.
Like a base
like a base growth. Yes. Or like a bacteria growth. Or like fossils. Hold on. Or fossils like decay. So you would use an exponential model anytime you're looking at a growth or decay model. Or population would be a growth model. Yes. So exponential functions look somewhat similar to functions you've seen before in that they involve crap. What do they involve? Exponent. Thank you. I told you I haven't read this. I woke up this morning and I said I haven't read teaching today. And I said, that's nice, and I'm not sure it works.
No, you can have a day off sometimes.
I know. But yes, it is way more work for a teacher to take a day off than it is to actually come to work. So fine.
No,
On average, if I sorry, this is my last personal. I know you're like, please get off now. On average, if I take a day off, it takes me about 4 hours to get ready for a substitute so I can take a day off. So if I'm only working 8 hours a day, and it takes me 4 to 5 hours to get ready for my day off, do I really have a day off?
Once they're putting grades that night, you can take a day off.
Okay, moving on. So there's a big difference in that the variable is now look at this. This is kind of the parent graph, how it looks. The variable is the x variable. It's now the power. It's now the exponent. It's now the exponent rather than the base. Exponential functions take the form y equals a times, this is a multiply, b to the x. When a is greater than 0, the value of b determined, I don't know what that means. Let's move on. I'll tell you in a second. Okay, so when hold on. Be quiet for a second. Be quiet for a second. Give me a second. When b is greater than 0, greater than 1, when b is greater than 1, the function grows. I just had it in my mind picture if it was going to be A or if it was going to be B. If B is greater than 1, the function grows. So again, some words that indicate growth would be interest, appreciation, increase, return to growth. Any of those would determine or would indicate that I'm growing. And this is what the parent function would look like. Now the steepness of it, it could grow faster or it could grow slower, but it still would be a growth. A decay model looks like this. So you're getting closer and closer to 0. Depreciation, decrease, decline would all be decay models. And I would recognize the decay model if my b is between 0 and 1. If it was 1, it would just be a line. So if we're looking at the end behavior, as x gets bigger, y gets bigger, right? On the decay, as x gets bigger, y gets closer to 0. So it doesn't go to negative, and then it bottoms out of 0. So we would call this over from asymptote, right? Alright, moving on. Exponential functions can be used to model many real-world situations, including half-life. You use half-life a lot in chemistry. I was like in one of the sciences, I was thinking biology, probably there too, but in chemistry you see that. Anyway, savings account. We're going to do a lot with savings account. Population growth probably. And then there is an example where we bounce a ball. Okay. So, let's look at what the different graphs could look like. This. Okay, so let's use this function y equals 2 to the x. Now, y equals 2 to the x is a different parent graph than y equals 3 to the x and y equals 4 to the x. So there is a pattern on how to graph them based on the base. in 0, I plug in 0 to the 0, which is 1, right? Now let's go up from there. Let's see if we can discover, hold on, it's my turn.
Let's break that for.
Okay, so let's see if we can discover what's happening between them. So if I plug in 1, 2 to the first power is 2, right? If I plug in 2, 2 squared is 4. If I plug in 3, 2 cubed is 8. So what's happening from here to here to here? It's doubling, right? It's doubling because of this. That's my growth. That's my multiplier. You can call it a multiplier. So that's the pattern. Now if I'm doubling as x gets bigger, what do you think I'm going to do as x gets smaller? I'm going to half it. So 2 to the negative 1. 2 to the negative 1 is the same thing as saying 1 over 2. Is that okay? So it's 1 half. 2 to the negative 2 is the same thing as saying 1 over 2 squared. That's what the negative does, right? Which is 1/4. As I'm going backwards, is it halving?
Yeah.
Yeah. So then this is what it looks like. At 0, the paragraph crosses at 1. At 1, I'm at 2. At 2, I'm at 4. At 4, or I'm at 3, I'm at 8. So it's just double, 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 double. And then half. Now if I keep halving it, will it ever cross the 0 line?
No.
No. This is why the asymptote is 0. Looks like that. Okay. This one, b is 1/3 in this case. So this one is a decay. So we expect the function to go down, get closer to 0 this way. Let's plug in a few things. Again, let's start with 0. So ignore the 2 for a minute. 1/3 to the 0 power is 1, right? Anything to the 0 power is 1. Now if I times that 1 by 2, I get what? 2. So that's 1, and then 2 times 1. So let's plug in a 1 now. So 1/3 to the first power is 1/3. And 2 times 1/3 is 2/3. Plug in a 2. What's 1/3 squared? You know? 1/3 squared, I square the 1, I get 1. I square the 3, I get a 9. So 1/3 squared would be 1/9. Multiply that by 2, we get what? 2/9. It's harder to see the pattern going from here to here. What are we doing? We're dividing by 3. So if I divide by 3 again, this should be 2 over 27. Dividing by 3 is the same thing as doubling the denominator, or as tripling the denominator. So if I plug in a 3 right here, 1/3 cubed is 127 times by 2. Now if I'm dividing by 3 as I go down, as I go up, what should I be doing? Multiplying by 3. Let's see if that works out. So, good, I'm going to do it right here. So if I plug in a negative 1, ignore this for a minute. What does that negative 1 do? It flips it, right? So that means 2 times 3 would be 6. So I divide by 3 going down, I multiply by 3 going up. Let's plug in the negative 2. 1/3 to the negative 1/2, or to the negative 2 is the same as saying 3 squared, which is what? So 2 times 3 squared would be 18. So let's plug that in, although I don't think we can put 18 on the graph. This is an 8. So at negative 2, I'm clear off the grid. At negative 1, I'm at 6. At 0, I'm at 2. At 1, I'm at 2/3. And then it gets closer and closer to 0. So it's something like this. A couple things I'd like to point out. This number right here, at the 0, that shows up, right? Does it happen, did it happen here? So what number would be in front of the 2 if I had one? It would be a 1 times, right? Is my starting spot a 1? Yeah. So if I were to make a general rule, go back up to here, the A, as long as there's no plus or minus out here, the A is your y-intercept. Now again, if there's a plus A or there's a minus h in there, it could change the y-intercept. But without anything weird going on, that A is your y-intercept. The B is your multiplier. Multiplier. That pencil sharpener probably needs to be empty. Okay, so let's go to the next page. What do you know for the domain, range, y-intercept of these functions? The domain is all real numbers. The range is from 0 to infinity, right? The y-intercept is 8. Okay, moving on. So, I really just want to graph. Hold on. Are there any graphs? Okay. No graphs? Okay. I really just wanted a graph. Example of growth or decay, and what is the y-intercept? So on this one, how I decide if it's growth or decay comes from here. Is it a growth or a decay? It's a decay. How do I know it's decay? It's less than 1. Good. And then what's the y-intercept? Y-intercept is my a value, 12. So if I wanted to get my next point after that, I would multiply the 12 by 0.95, and it would go down a little. And then I'd multiply by the 0.95, and it would go down a little. And I would multiply that number by 0.95, and it goes down a little bit. And it ends up looking like a curve. What about the next one? Is that one a growth or a decay? This one, because of the 2, is a growth. And my y-intercept would be? Point what? So if I were looking at this graph, this is 1, 2, whatever, I start at 1/4. You don't have to draw this, but just watch. I start at 1/4. When I go over 1, I would double it. What's double of 1/4? 1/2. And then I double it again, which would be 1. And then I double it again, which would be 2. And then I double it again, which would be 4. And you see how that makes the curve? Because you're doubling each time? Yeah. And then if I were going to the left, I would half it, and then it goes down. Okay, moving on. You put $1,000 into a college savings account for 4 years. The account pays 5% interest annually. Would that be a growth or a decay? Well, that better be a growth, right? Now, what's the initial? What's the starting spot? What would be the y-intercept? You start with $1,000. Good. So the y-intercept would be $1,000. Okay. So key concepts. Just to kind of just put it all together. You can model exponential growth for today with this function. A of t is the amount after t years. It's kind of like saying f of x. So the amount after t years. A is the initial amount. 1 plus r is the rate of growth or decay. And the t is the time period, so number of years. So we would use this model if I were dealing with just a growth model or a decay model. In a couple lessons, we will be doing a continuous compound, and we'll talk about that. We use a different equation. So this is one of the first ones you need to remember. For just a regular growth, it's a times 1 plus r to the t. So let's try a few examples using that formula. You spend...
Remember, hey, that came up with all the grammar. Sixth grade, that was,
My grandma was kind of, my grandma had a lot of health problems, and she had no, like, her peripheral vision was gone, so she kind of had blinders on. It felt, you'd stand right next to her, she couldn't see you. Anyway, that doesn't matter. She would give us for Christmas every year, like in those little tiny, like, stockings, those little red ones, like $5 bills every year. I'm like, thanks, Grandma. Anyway, this grandma is nice. You deposit, okay, moving on. You deposited $1,000 in the savings account at the end of the 6th grade. The account pays 5% annual interest. So this number is probably important. This number is probably important. How much money will we be in the account after 6 years? So let's first label all of our variables. What's this one? This is A. That's your starting point. That's your initial amount. This is your R, but I'm not going to put it as 5%. How do I write it? 0.05, right? Well, R is 0.05. And then we'll put the 1 in, because it's the formula. And what about this? I'll let it bug you. That's the t. So we plug it into our function. If I want to know how much I will have after 6 years, I plug in the starting amount times 1 plus, now do you have to write it like that, or could you put 1.05?
1.05.
You could just put 1.05. Kilowatt power. Okay. Plug that into your calculator, what can you get?
That actually costs $1,000.
Here, come on.
Yeah.
Into your calculator. So we're hoping that we get a number bigger than 1,000, right? So that's when we have a 1. So what did we get here? Don't eat. 1,340 point dollars. So after 6 years, we get $340. So when they graduate, they've increased their money by $350. Try the next one. Suppose your parents invested $300 in a savings account the day you entered kindergarten and didn't deposit any more throughout the school years. How much money would you have in your account when you graduated from high school? The account pays 3.5. So what is the 300? The initial, and what's the 3.5? So this is your A. This is your R, but R is what? 0.035. No, R is 0.035, right? T, we know where you're getting the 1. The R is technically 0.035. I really don't care what you do. Now, what about the time? They deposit it when you enter kindergarten, and they take it out after you graduate. How many years is that? 13, right? So you have 1 to 12 plus the age, it would be 13. So your time is 13 years. So, my amount after 13 years is what? 300 times 1. 0.035. If you forget the 1, it's going to look like you have almost nothing. It's the 1 that makes it grow. Remember, without the 1, it's a decay model. So the 1 makes it grow. Raised to the 13th power. And this is where we learned that we should have deposited more money. Right? Because how much do we have after 13 years? Say it again. So, do you have more? Yes. Do you have enough to pay your first month's rent? No, not really. Okay, any questions? Even then it's questionable. Any questions with that? Yes. Okay. Any other questions? All right, moving on. Give me 1 second. You invest 1,000, or no, just kidding. We're not even going to start this because it is pretty much lunchtime. So I'm going to pause this, figure it out, and then when you get back, I'll be ready to teach it to you. Okay, part C. You invest $1,000 in a savings account that pays 5% annual interest. If you make no additional deposits or withdrawals, how many years will it take for the account to grow to $1,500? So, it is easy to roughly figure this out on your graphing calculator, so let's get that open. Let's find mine. Yep. I don't know where my graphing calculator went. So here's what you do. I guess I can't really do it with you. So the first thing you want to do is to go up into the y equals button. And you need to plug in the equation that fits this scenario. So using the formula from before, the 1,000, what is that? We need 1,000, we need the 5%, and then t is time. Or x is time, I guess. So this is my a, right? This is my what? R? So what would the equation be? It's going to be y equals a times 1 plus r to the t. Okay. So instead of t, you need to x to the right. I'm sorry, I don't know where my graphing must have I don't have my figure projector. Okay, so are you in the y equals? Can you plug that in? Now, over here, which is hard to see on mine because the picture is blurry, but over here, the button, it says graph, right? Above the button, it says table. Do you see that? Yes. So instead of graphing it, put second table, and it should come up with something that has x and then y1. Does it? Yes. Yes, because I went from a percent to a decimal. Alright, are you with me? It's hard to tell because I don't have one. Are you okay? So you have a screen that looks kind of like this with an X right here and a Y right here. And it has 1, 2, 3, 4, 5 and then a bunch of numbers. So we want to know roughly how long it's going to take to grow to $1,500. So where on here is Y $1,500? Or above 15? It looks like at year 8 it's 1477, is that right? And then at year 9 it's 15 something? Yes. So it's not going to take 8 years, that's not enough, right? So we're going to say it takes how long? 9 years. Anybody have a hard time finding that? Anybody else need help with their calculator? So first, you're on your right one. So plug that equation 1,000. And then the second table. Anybody else need help? do that again. Part D, you invest $500 in a savings account that pays 4.5% annual interest. If you make no additional deposits or withdrawals, how many years will it take for the money that you have in your account to double? So what do I do with this question? Okay, so y equals what? 500 times 1 point. Good, so the t is going to be x. So you plug that into your graph, or to your y equals, and then what? Then you go to the table, and you're looking for what value? You want your amount to be 1,000. You want it to double. Years for the double. Make no additional payments. It's going to take you 16 years to double the money. So, I'm sorry I can't show you that. Did everybody get 16? Try it. How come I didn't know this? Well, okay, thanks for me. That works for me. Okay, last one. Are we recording? Good. You'll need it for this kind of stuff. Other than that, your okay. Last one. The Iberian lynx is the world's most endangered feline species. Pause really quick. Did you know there's only 1,000 pandas left? Like 1,000. Like the panda bear? There's 1,000. There's only like 20,000 African lions or something. Like, it's not very many. I can imagine there's only 1,000 left. It's funny you say that word. Say that one more time. To buy a panda? What would they do with a panda? Fantastic. Great. All right, so this lynx is the world's most endangered feline species. That's what she looks like. In 2003, the population of the lynx was 150, and in 2004, it decreased to 120. I got these numbers online, actually. Now, we can predict what's going to happen. The prediction actually is a little bit different. I don't remember what it was. I looked it up last year, but I forgot to this year. Anyway, so in 2003, it was 150. In 2004, it's 120. So are we okay saying that it decreased? How? Well, let's read. It's feared that the lynx will be the first cat species to become extinct in nearly 2,000 years. If this trend continues and the population is decreasing exponentially, how many Iberian lynx will be there in 2014? So the first thing we need to know, do we know A? What's the initial amount? 150. Times 1 plus, do we know R? We need to figure that out, but we're going to skip that part for a second. Do we know X? So in 2003 is our starting spot, 2003 to 2004, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 11 years. Okay. So how do you find R? The formula for the rate of change, down here. So I don't remember when he would have learned this. I remember before the core change, I think you get my 7th grader. To find the rate of change, you take the change and you divide it by the initial amount. So if you're going from 150 to 120, how much did that change? Negative 30, right? So it went down. And the initial amount is how much? 150. So that is what percentage? This is a 20% change every year. It's decreasing by 20%. going down. So, if I want to know how many there will be in 2014, here's what it's in. 150 times 0.8 to the 11th. How many Iberian links will there be in 2014? Say it again. Why 0.8 was because are you okay that the change is negative 0.2? And when you plug that into the 1 slash and then the R? Now, if you go back to the very beginning of the lesson, we said anytime this number is less than 1, it's a decay, right? We expect this to go down. Can somebody plug that in? 2014. 7.4, like 7.4? Somebody confirm, is that what you got? 12.8? Now we're not going to say 0.8, right? Because there's probably not 0.8.
The bus is lost its way.
It's one-handed. If it continues to take. So, when you brand it, it's not appropriate. Branded is not appropriate. Okay, so if it continued, I talked about it. We're doomed. Okay, thanks for watching. Peace out. Oh, just in case you're wondering, I did look this up last year. In about, I can look it up again. I think about 2008-9, obviously if you're seeing a decrease in species, there's going to be some conservation efforts. They are still alive and living, just there's not a lot of them. So